But want to review some stuff before we get into the homework. Um, so if you don't mind closing your pewter lids, that'd be great. All right, Coulomb's law, we worked this out a bunch. Force between two charges is proportional to distance between them, so that's good stuff. Want to remind you about the electric field, so really close in to a charge, like that close. Notice it's sort of like Goldilocks and the big bad wolf or whatever, how big the electric field lines are, okay? So really in close, you have these humongous electric field lines. We sort of saw this in the simulation the other day. If you go out farther at this distance, they get smaller. And then all the way out, these are all equidistant. And so that's that inverse square action going for us. And also note that for a positive charge, all electric field lines emanate from positive charges and terminate at negative charges. So we have, our positive charge, everything is going away from it here, and and you can sort of see that just strictly as opposed to um, uh, without any particular distances. So they emanate out from positive charges, and all of those will someday, somewhere, at some point in space and time, terminate on a negative charge. All right, that's the basic idea. See some field line pictures in a minute that make sense. Now, this is a setup for a lecture that I don't know if I'll start today. Certainly Wednesday on electric dipoles, which you studied in chemistry. So we're going to apply the physics to something you already know a little bit about. But dipoles get torqued. So in an electric field, these two charges that are part of a dipole will react oppositely in an electric field. Therefore, they'll turn, they'll wobble. So this is happening constantly in nature because nature's got a lot of water in it, and there's a lot of electric fields in living critters from their sodium, potassium pumps, you name it. So molecules are getting wobbled, polar molecules all the time. And that has some impact on biological function. More on that later. We did this with the sticky tape. And so if no excess or deficient charge, no interaction. But if you rub them, meaning friction, then there's a deficit of charge, or in some ways the same charge, and so you get this sort of deflection when you do it. And we saw this with the tape. This is just another set of objects, same interaction. Friction causes electrons to be removed, period. Opening up positive cores and giving you a net positive or negative depending on what you rub and what you rub it with. And then it can be attractive, same way. So does this just review stuff, different ways that we could do this. I'm going to skip through some of this, but it is worth noting what we mean by neutral. A lot of times people kind of check out on what is meant by neutral. Neutral doesn't mean no charge. Neutral means same amount of positive and negative. I suspect this is old news from chemistry. Yes? All right, so don't have to labor that point. When they write textbooks, you write them to be independent of people's preparation, or best you can. Nice thing about this physics course is by the time you come to this course, you've already had plenty of that other stuff. But anyways, uh, this thing charges on a conductor, adjust until there's no net force on any charge. Okay, and that's what we mean by electrostatic equilibrium. Um, Equilibrium is always zero net, basically. And that'll be some of our problem solving. Then there's this charge model. So we haven't formally stated what we mean by all the stuff that we've done in terms of lab um, and stuff you've been reading, homework, et cetera, et cetera. So let's take a moment. Frictional forces add something called charge to an object, or they remove it from the object. Okay? And we do, in fact, call that process charging. So charging, you're used to plugging in, uh, a cord and into the wall and the cord into your phone or something, and you charge the phone. But it's not like friction, is where electricity comes from in that regard. We're talking about static charge. I think before today, at least I hope, before you came to college, you knew that there were two kinds of charge. Um, that's sort of a no-brainer. And like charge exert repulsive forces, and opposite charge exert attractive forces. We know that, and we call those electric forces. Force is just one way to describe an interaction. You won't find that in any textbook that I'm aware of, but force, energy, they are ways to describe an interaction. Period. And no matter what kind of force it is, contact force, friction force, electric force, magnetic force, strong nuclear force, it's one way to describe an interaction. Energy, momentum are other ways to describe those same interactions. Less important is that it's a long-range force, infinite as far as we can tell, but it can only be transmitted at the speed of light. So the farther away it is, still going to get there no faster than the speed of light. We just talked about neutral objects, and you knew that from chemistry. And then obviously, at least I hope it's obvious, frictional forces are transferring charge. We only said this once, I think, the charge conservation. One would hope that you would expect charge to be conserved, given that charges produce forces that cause displacements, which means we're talking about electrical energy, which is our next topic after we continue charge distributions. And so energy is conserved. So there's all these conservation laws: mass, energy, momentum, etc. All right. Conductors and insulators. Conductors have free electrons, meaning there's a mobile electron C. We're going to have a whole lecture or two just dealing with how that relates to current in circuits, such as the current that's in and out of these light switches. Okay, there's a mobile electron C. I mentioned that briefly the other day. And then contact, we can transfer that way. That's the charge model, has those elements to it. Let's talk our way through a couple of things here. So if I take a piece of charged plastic and conduct, if I touch, then that metal sphere will acquire some charge. It will transfer whatever excess charge is on that plastic, will equalize instantaneously, effectively instantaneously, at least at these very, very short distances and small amounts of charge, and they'll equalize. On the metal sphere, it'll perfectly, every charge, if we could see them, they would be equidistant apart because they all want to get as far apart from one another as they can. And whatever's left on the plastic rod will do essentially the same thing over all the parts of the rod that have uniform curvature. On the edges and high curvature, it's different. We'll get into that later. Okay. Um, Here in this next one, plastic rod's not transferring because it's not going to transfer. All right. And then if you have a metal rod, because they conduct, then charge, will, if it's negative charge, it'll fly off of there and then fly over here and come on here as well. So, um, and it'll just equal out. And the more space there is to fill, the farther apart those charges will get. It'll happen faster than that. All right, basic stuff. Pretty sure you guys already know about that, so I'm not going to labor that. But I do want to remind you, and hopefully this makes some sense in chemistry. How much time did you spend thinking of molecular bonds and those forces as like spring forces? So I know you had the stick and the ball models that you play with in there, correct? And those sticks and their angles and how long or short they are indicate the strength of how they're bonded or how they're constructed in the molecule, depending on what you're paying attention to. And so uh, friction can literally break up these bonds. And those bonds have energy associated with them, binding energy, if you will. And so that's where the heat comes from in that transfer. Um, but this is a review lecture, so it won't take us too long. Let's get more down to the chemistry, so to speak, physics of this insulator versus conductor. So, key difference, these valence electrons, which you should know plenty about, in an insulator, they're stuck real tight to the atom. All right. Whereas in a metal or a conductor, they're free. They get to move around. Since they're free, a weak electric field as well as a strong one will make them move through the metal. Actually, they move along the surface, but that's another story to that. So I'm going to bank on your tree knowledge, not forcing us to do this. So electric dipole. So here's some atom, okay? And before this external charge came into the picture, this would have been over here in the center. But as soon as that positive charge comes near, then obviously the positive charge in the center of the nucleus wants to get away from that. And the electrons, they want to get to where this other positive is. So this, if you could think of an atom, which you can sort of, the electron shell is like a bubble on it, so to speak, though it's not a material bubble like we think of, but it sort of contains that whole thing. And so this is, if you could think of, some sort of spring connection, which isn't a bad way, to think of how electrons are connected with the nucleus, all right, then those springs are getting stretched. And if you keep stretching a spring over and over and over again, well, it's going to get hot. And if you stretch it far enough, it'll snap. All right. And so we can break up. We could have something, such a humongous charge that it would literally rip electrons off of nucleus. That's conceivable. Like if you had a 1 coulomb of charge on, say, a metal sphere and you brought it near something, it could literally rip the outer shells off of everything in that piece of material. That's how much a coulomb of charge would be at a short enough distance. I think we did a problem like that in one of the other lectures. Um, so anyways, we did this already, Coulomb's law. In fact, we built it ourselves, and we noticed this with the tape. We had repulsive tape, and we had attractive tape. Plus, and you already know about there's two electric forces are attractive and repulsive, whereas say something like gravity is just attractive, and that's because mass. There's only one kind of mass, whereas there's two kind of charges. Two and only two, technically. So again, this is a review lecture. Now, this review lecture has some clicker quiz stuff, except we're not going to use clickers because we ain't got no clickers. But we're going to check some understanding here. So here in this picture, so think through this. Some small positive charge is placed where this black dot is in these four scenarios here. In which case is the force on the small positive charge the largest? So a small positive charge is placed at the black dot. These four options here. In which case is the force on the small positive charge the largest? We have some takers on C. So if I put a charge, so I guess here's the thing is, I don't know what the charge on the black dot is, but it's the same in all four scenarios. The charge on the black dot, the black dot is what it is. And so if I just look at, let's see, A and C, which one's a larger charge or a larger force? C. Why? Because I have more charge on the other one. So we could just say that the black dot has a charge of 1, just to make it simple. Because it doesn't matter what it is, it's the same in all four scenarios, the charge. Now the force interaction is based on what? The force interaction is K Q per R squared. So A can't be the answer because it's smaller than another one. And then these ones that are double the distance away, seems like they would be smaller as well. Because if I were to do this one, the 2R, that's 1/4. This one here would be QQ per 2R squared, or 1/4. So we have an answer. Let's see what the drum roll, please. Oh, C. Yay. So the point here is why is that the right answer? And what you have to do is realize, okay, it doesn't really matter that I don't know what the charge on the black dot is. It's the same in all cases. So the closer I am, the bigger the force, and the more charge there is on the other one, the bigger the force. So in C, I have both. Biggest charge relationship possible, shortest distance possible. Therefore, biggest electric force interaction. And by the way, the electric force on the big one is the same as the electric force on the little one. Because Coulomb's law is product of the two charges over their distance squared. They equal and opposite forces. That's how those electric fields are acting. All right. Next question. Same situation. In which case is the force on the small positive charge the smallest? So let's think about my reasoning. Let's see if that works out. If it's the case that the farther away it is, and the smaller the total charge is, that should be the smallest force. So which one has both longest distance, smallest amount of charge? somebody at the middle table take a swing at this. Which one? I can't hear. Which one has the smallest force? Which one? Well, wouldn't it be the case that the smallest charge product? Well, it has to be B or D because of the distance. And then which one has the smallest charge product? Huh? D does. So hopefully our reasoning towards D is correct. There we go. So again, it's the reason why you picked that. That's important. No math to do really when it comes down to it. All right. Just sort of in your head. All right. All charges in this diagram have equal magnitude. A small positive charge placed at the blank dot, that should be the black dot. There we go. In which case is the force on the charge to the right? So we're looking at, which one of these black dots, if that's a small positive charge, which one of those is going to get pushed to the right? So this this negative one in part A, okay, it's going to pull this positive charge in, and let's say that that's how strong it pulls it in. This one for A is going to push it to the right, but the net, it won't be as big, right? Because it's an additional unit away. It's twice as far away, so its impact will be as a fourth as big. So the net effect on this one is to the left, so I'm guessing the to the left is going to be A, because that's the net effect there. So I think somebody was saying B. Looks like we'll have a big push there. The positive's going to push that to the right, and the negative is going to pull it to the left a little bit. So it looks to me like you're probably right, that B is to the right. And then 0. Which one's going to be 0? Yeah, I think D, because this one's going to get pulled that way and that way equally. So that should work out that way. And since we don't want to leave this out, it should be fairly obvious that in part C here, it's going to get pushed to the left by a positive charge will get pushed to the left by 2 other positive charges. All right. So I guess I didn't put the answer key in. This one, isn't it the case that that's going to be a less than 1 because of the difference? That's also going to be a less than 1 magnitude. That's a 0, but this one went over 1. But will be what it is. All charges are equal magnitude again, in which case is the force on the small positive charge the largest? Somebody said what? Well, I think if we look back to, so C will be the correct answer. And that's because I'm adding, uh, there's no difference to sort out. I just keep adding on in the same direction, whereas there's some cancellation in all other three. One of them has a net zero, two of them have a net that's smaller than the biggest force they're in. All right. Oh, didn't we just smallest? Well, I guess we already answered that, right? Zero be the smallest. So we sort of have our answers from the analysis of the one problem. All right. Electric field. Let's go a little bit deeper in electric field business. Um, in the force model, A exerts a force directly on B. So a charge will exert a attractive or repulsive force on some other charge. So I did make some emphasis on charges don't exert forces on themselves. They exert forces on other charges. All right. Uh, this field model alters the space around it. So if you think back to the movie with Faraday, and they were scoffing at him initially, but then he got the last laugh on him. Okay. He imagined these invisible lines of force emanating out from a moving charge, and that was magnetic because it was deflecting a needle. Okay. But electric fields and magnetic fields produce the same kind of distortions in space as far as we know. That's our model. And our model is extremely good at predicting all sorts of outcomes, medical imaging, you name it. If it's a lie, man, we have tricked ourselves really good for a very long time, and everything works really great with the trick. Okay, so it doesn't. Even if it's not the whole truth, it's enough. All right. Uh, and then I think the idea here is this particle would respond to the altered space, and so imagine if you were standing on the ground when an earthquake. Anybody ever seen those things where it looks like the ground sort of turns into like jello and it it doesn't break up, but it gets all wavy like it's water or something. Okay, certain kinds of soil and whatever will do that. And if you were standing there, well, that could be bad for you. All right, you get sucked into the ground or whatever, and the ground would literally what you're on, that surface would be changing while you're on it. Or if you're out on a boat and you get into a choppy seas, guess what? The surface you're on is changing, and therefore your interaction with it will change. Same with charged particles. So the thing to get out of this is these electric fields alter the space, and then things that react to that, like an electric charge, will move accordingly, just like you would if the ground underneath you started waving. All right? And we've already sort of seen this a little bit, and the reason I'm bringing this out here is because the lecture on charge distribution is going to be a 3D vector set of algebra, and I know you're excited, so hold your applause all right. We sort of seen this in the simulations that we were working with, and if you recall, we had those charge sensors, and they would give us some sort of arrow when we were playing with the PhET simulation. So we like to use a positive test charge, and these physics questions about electric fields and forces. So get used to the idea of what would a positive test charge do if placed in a field. If it's placed in the field of a positive charge, it will go away from the positive charge in the direction of the field. If a positive test charge, like the one I've highlighted in yellow, is placed in the field of a negative charge, then it will be attracted the opposite direction, towards it, against uh, the normal field, if you will. So, but Field of a positive charge is always going to go that way. If I put an electron, which is a negative charge, and they're blue, by the way, it's still the case that the electric field going out from that positive charge is going that way, but the force on the electron is going to be opposite the field. So I'm saying this because there's questions and whatnot where your thinking needs to be something like what I was just saying. All right. Electrons will move opposite to the field. Protons will move, or positive charges will move with. All right. More questions. Now we're doing good. We're doing good. Positive charge created an electric field. Which case is the field at the black dot the smallest? So the last time we did this, it was force is the smallest. Will it be any different? Remember, electric field is defined as kq per r squared. So now these dots, they're not charges, they're just a place in space. Has anything really changed? Isn't it still the case that the bigger the charge and the smaller the distance, the bigger my field? And the bigger my distance, the smaller my field, as well as smaller charge? So which case gives me both smallest charge and biggest distance? Wouldn't D have smallest charge, because I only have Q and 2Q, so Q is the smallest charge, and the biggest distance is double the smaller. So hopefully it's our right answer here, and it is. I love it when I get the right answer. I get to keep my job. All right. So, because I've never seen this lecture slide before in my life. Just magically appeared in my computer. All right. Then the largest, so the opposite. Biggest charge, shortest distance. I'm guessing C. Bingo. Woohoo, all right. And then, so we're kind of repeating things, but with respect to field. So far the answers have been the same, as I recall. Net field, well, if the forces were, if the net force here was this way, and the net force here was that way, and that, well, wouldn't the fields be in the same direction? Yes, because electric force as a vector would be defined as charge times field. So we've already seen that Coulomb's law told us this. And if I do force per unit charge, that's what electric fields are. So this critter right here, hopefully you see that F would just be QE. If I solve this for F, I just get Q times E, which it's just a compactified version of Coulomb's law. All right. And the key idea here is that the thing that's generating the force has to be in the same direction as the force it generates. Or the force generated by the source has to be in the same direction. It can't be off in some other direction. That would make no sense. That's the utility of this. All right. In each of the four cases below, we consider electric field to these two charges at a point. In which case is the magnitude of the field, the black dot, the largest? Looks like we got a new situation here. So let's so there's let's put it on the charge. So coming from the plus, that's the electric field due to the plus charge. And because it's emanating from the plus charge. So it's going back to the picture we were dealing with earlier. And this negative charge, well, what's it doing? It's pulling in. All right, so it's kind of doubled up there. So we'll hold on to that idea. The plus charge here is producing a smaller field at that distance because it's twice as far away, or 1/4, if you will. And the negative charge, it's pulling in. So it looks like A is bigger than B. So it looks like B's out of the running. Then this one looks to be from there, and switch up colors here. This other one would add a smaller amount there. So I'm guessing, looks like C might be our winner. Bingo. That's a +2. And so what probably needed to happen was, instead of drawing it the way I drew it, I should have tagged the vector arrows one on top of each other, indicating a bigger field at that point than otherwise done. So this is a +2, and I think you can see that, this one and that one, they're same length, that's a +2. This has to be a 3/4. This is a 1 1/4, and that'll be a 0. So it's easy to mislead yourself. The net effect is 0 because they're opposite. So that one's pulling it in, and that one's pulling it in. So 0. No! What did we do wrong? So A is our big one. So you could put numbers on this if you assume, rightly, equal distance, and the magnitudes are plus and minus are all the same magnitude, just different directions. Right? Smallest. I guess we just determined that. So no need to labor that point. All right. Looks like my slide got chopped in a weird way. Oh well, fix that later. So I want to draw your attention to this charge distribution, if you will. This is a dipole, a crude, choppy picture of a dipole. And a dipole is just simply when you have a plus and a minus charge very, very close to one another, and you're paying attention to the field at a distance that's relatively much, much farther away. And you have a dipole. So water's molecules or dipoles. There's a lot of um, things like that. And you spent some amount of time in chemistry doing that. Uh, we like to have the dipole direction be this way, and more on that later. We are going to have a whole section on just capacitors. Okay, so we're going to cover that element later. But we did this the other day. We built a capacitor when we were studying. Remember when you lined up a row of plus and minus charges and the field between it was relatively uniform? If we'd have put more charges in there, it would have got more uniform, but we kind of spread it out. You basically built a capacitor, so to speak. And capacitors are basically electronic shock absorbers. Anybody have one of those stereos that will give you a back rub from 50 feet away? Or know somebody that does in their car? And they have these big capacitors that can blow if they thump it a little bit too hard. Well, capacitors do that. They can take a huge surge of charge and absorb it and then let it out slowly. That's a oversimplification of that. So moving on. Which one of the noted points is the magnitude of the field greatest? So what I want you to think of is if these were lines on a map, like of a mountain, where would the slope be the steepest? A, B, C, or D? A. So the idea is where the field lines are the tightest, that's where the field is the strongest. So it's sort of like a magnet would have this sort of field picture coming out of the end, and the closer you get to it, that's where it's the strongest. So you could think that same way about it. But if you were to take a gravitational field force example, which lines on a topographic map indicate that indirectly. So if this were a map of a hill, this is where everything's the steepest. Therefore, it's the strongest field in that region. So just conceptual stuff. And then the smallest inevitably would have to be out here where the lines are apart. Okay. We've hit this already, so I'm not going to labor that except to say in this capacitor business, because of the way you set things up, you get straight electric field lines. Normally out in space, they would never really be parallel, at least not for long. They would be twisted, diverging, or converging, depending on which charge you were heading to. But in a capacitor, you get them straight from point to point, and that's what we call a uniform field. So more on that later. So I'm just reviewing mostly today, previewing a little bit, namely with capacitors, a big deal. Let's looky here. Two parallel plates have charges of equal magnitude but opposite sign. What change could be made to increase the field strength between the two plates? Decrease the distance. That would do it because the force would get a little bit bigger. Anything else? Of the charge? Okay. The distance ain't, increasing distance won't do it. Taking away charge will minimize the force. Well, ooh, somebody remembered the equation. The capacitor field equation is essentially that. There's a there's a constant in there. It's charge per unit area. Okay. So increase the magnitude of the charge on both plates is the answer for increasing field strength. More charge, more field for a capacitor. So the distance ends up not mattering. It's charge and area, and that's a change, and we'll explain that more deeply as we move forward in the course material. What would decrease the field strength? Decrease the magnitude of charge. The reason that the distance don't matter is something we are glossing over for the moment. Um, the non-illuminating answer is that for a capacitor, it ain't in there. Now, why it's not in there, that's to be revealed later. One thing that's hard to believe, and we'll spend more time on later, is why for a conductor, the electric field at the middle is nothing. All the charge goes to the surface. And on some level, I think that might make sense is because this charge here, for instance, it wants to get away from that charge there. And this charge here wants to get away from that charge there. As do, every adjacent pair of charges want to get away from each other. But in the big picture, charges opposite one another, they want to get away. So they're not going to hang out in the middle. They end up going to the surface. Of course, in the middle, everything gets stuck in between atoms, but out on the edges, they can move to the surface, if you will. All right. So that's the short way. And then for the negative, they're terminating there, so they're not gonna. It's not like they're going to keep on going through it. That doesn't happen ever. We just worked this out a minute ago, so I'm not going to labor that. However, I do want to talk about torque on the dipole that causes it to rotate. So in an electric field, so this electric field, okay, that this dipole finds itself in, the positive end of the dipole wants to go that way. The negative end of the dipole wants to go the other way. That means this dipole is going to wobble in that field. And if that field fluctuates, then the wobble of this dipole, polar molecule, whatever it really is, will do that. And so, again, to draw this back to the domain of professional options that this group is interested in the medical sciences, generally speaking, your bodies are littered with electric fields. And given that you have a fair amount of water in you, there's a few polar molecules floating around in there being rotated in electric fields. Every time your entire nervous system is essentially a set of capacitors. That's an oversimplification, but a decent one. And sodium potassium pump, another builds up charge, exchanges, muscle action. All right. Kind of notice each end of the dipole in that configuration has the ability to rotate. It can experience a differential force. This one, of course, I didn't say it, but apparently maybe somebody noticed it. I was trying to trick you. All right. And it sort of halfway worked. All right. If it lines up, what can be torqued? So dipoles held motionless in a field for the situation below when the dipoles released. Which of the following describes the subsequent motion? Either it moves to the right, it moves to the left, it rotates clockwise or counterclockwise. I guess it could remain motionless. Trick is, which one of those things will it do? Well, didn't we just see that it's going to rotate? So probably guessing that it's A and B are out. And so trick is which way does it rotate? To the slide, why? Oh, it remains motionless.
Well, isn't it because it says when dipole lines up with the electric field, which it is right there, it remains, the torque remains zero, so it remains motionless?
Right. So if we go back, so much for freaking the class. I tried. All right. This one, I guess, is the other example. So we expect it to rotate counterclockwise. And why is that? Well, this one wants to go that way, and that one wants to go that way. And last I checked, that leads to a counterclockwise torque. If we switched them, it'd be a clockwise torque. Okay. I guess that's the clockwise torque. There we go. So that's the summary, and this is all stuff that we've hit in other lectures, so I'm not going to labor that point no more. So end of that.